The universe is expanding. That has been established for nearly a century. What is not resolved is how fast. Two independent methods of measuring the expansion rate currently produce incompatible results. The disagreement is not small enough to attribute to measurement error. It is large enough that physicists have given it a name: the Hubble tension. The first method uses the cosmic microwave background, the faint radiation left over from the early universe, emitted roughly 380,000 years after the Big Bang. This radiation contains a detailed record of conditions in the early universe. By analyzing it and running that data forward through the known physics of cosmic evolution, astronomers can calculate how fast the universe should be expanding today. The Planck satellite mapped this radiation with extraordinary precision across the full sky, producing one of the most detailed measurements in the history of cosmology. Multiple independent analyses using this method converge on a value of approximately 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.26 million light years, the universe is expanding at 67 kilometers per second. The second method measures the expansion directly, using objects at known distances and known intrinsic brightnesses, primarily Type 1, a supernovae, and a class of pulsating stars called Cepheid variables. Astronomers use these as standard candles, objects whose true brightness is known, so their apparent brightness tells you how far away they are. This is called the cosmic distance ladder. By measuring how fast distant galaxies are receding, you can calculate the expansion rate without relying on early universe physics at all. Multiple independent analyses using this method converge on a value of approximately 73 kilometers per second per megaparsec. 6 is a small number, but in this context, 6 represents a gap of roughly 9% between two measurements of the same physical quantity derived through completely independent methods, each refined over decades to eliminate error. The gap has not closed. It has become one of the defining open problems in modern physics. It has grown more statistically significant as both methods have improved. The Planck results became more precise. The distance ladder was recalibrated with data from the Hubble Space Telescope and later the James Webb Space Telescope. The tension persists and in some analyses has grown. If either measurement contained a systematic error large enough to explain the discrepancy, that error should have surfaced by now. Multiple independent teams have examined both methods. Some physicists have proposed that dark energy is not a cosmological constant, but evolves over time. Others have proposed early dark energy, an additional component active in the first moments after the Big Bang. Others have suggested new neutrino physics, modifications to gravity, or errors in how distances are calibrated across cosmic scales. None of these explanations had been confirmed. No single proposed solution is widely accepted. The two best measurements of the universe's expansion rate do not agree. The standard cosmological model cannot currently account for both simultaneously. Something in our understanding of the universe may be fundamentally wrong.